Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 2, Part 9, and we are in the third section, Mixtures and Solutions. So mixtures are different than elements, and mixtures are different than compounds, which we've been talking about. They are not pure substances, which means they can be separated by physical means like filtering, evaporation, and other physical means. So mixtures, there are two main types, heterogeneous and homogeneous. And in heterogeneous mixtures, the properties are not uniform. So this part of the mixture is different than this part, which is different than this part, which is different than this part. So some examples, and please write these down. Granite is heterogeneous. I'll show you a picture of that. Okay, so you've got the granite, and you can see these little black bits are different. That's the mica, and it's different than these little pink bits, which is the feldspar, which is different than these little white bits, which is the quartz. So it has little pockets of different composition. Also, blood is not uniform. You have your plasma and your red blood cells and your white blood cells and your platelets. The same with trail mix. You got your peanuts and your raisins and your M&Ms, and they are not all equal or the same. And then you have oil and vinegar, again, not uniform. They will separate out. So opposite of heterogeneous is homogeneous, where the composition and properties are uniform. So they are the same all the way through, and these are also called solutions. So some examples of solutions are air. So if I were to breathe air over here, it's going to be the same 70% nitrogen as if I were to breathe it over in that corner over there. Kool-Aid, if you mix it up, that's evenly distributed from the top to the bottom, same as sugar water. All right, let's take a look at your book on page 56. So we can see in our images that well-mixed food coloring is a homogeneous mixture. The composition is the same up top here in the red one as it is on the bottom right here in the red test tube. Concrete is an example of a heterogeneous mixture. The composition is not the same. You've got some big chunks here and then some small chunks over there that are a different mineral. Let's look at this table 2.1. A homogeneous or homogeneous mixture is a mixture that contains more than one type of matter and is the same throughout. Examples are soda pop, air, and metallic alloys, where you have a couple of metals mixed together. A heterogeneous mixture is a mixture that contains more than one type of matter and is not the same throughout. So chicken soup, you've got those chunks of chicken, the noodles. Soil is you've got chunks of sand and clay, and that's going to be different throughout. And fudge ripple ice cream, definitely not the same all the way throughout. We're going to contrast that with elements, which is a substance that contains only one type of atom. And any of those elements, any of those 118 elements would be examples: copper, oxygen, nitrogen. And a compound is a substance that contains more than one type of atom, and then those substances, those atoms have been chemically bonded together. So table salt, sodium chloride, rust, iron oxide, and carbon dioxide are examples of compounds. We've talked about mixtures before. Let's hone in on solutions. So this is a type of homogeneous mixture. A solution always has a solvent and a solute. The solute is the substance dissolved, and the solvent is the dissolving medium, and it is almost always water. It can be something else, but in chemistry and in life, water is the most frequent one. So a way to remember this is you put the solute in the solvent to make a solution. So I want you to think about salt water and take a guess. Write this down, please, and write down your guesses. What is the solute? What is the solvent? And what is the solution? Okay, if you said salt is the solute, you would be correct. It is the substance being dissolved. If you said water is the solvent, that's right, it is the dissolving medium. And then our solution is salt water. When solute particles are evenly distributed throughout the solute is considered dissolved. And solutes dissolve faster at higher temps. Why do you think this is? It is because solvent molecules at higher temps are moving faster and are better at knocking solute molecules into the solution. So please write that down. So let's take a look in your book on page 57. We have an example of a solution, which is orange juice. And if it has the pulp, it's heterogeneous. But if it's the non-pulp, then it would be homogeneous. So the solvent is water, and then those solutes are the sugar, calcium, iron, ascorbic acid, potassium, citric acid, and all of the orangey stuff in there. So looking at sugar water, we have our solute, which is sugar, and then our solvent is water, and then the solution is sugar water. And you can see what's happening when the water dissolves the sugar is these little water molecules come around and they surround each sugar molecule. And if the water is hotter, we know that those sugar molecules are moving faster, and then they're more likely to knock one out and get it over, get it separated from its group so it can be surrounded by water. So hotter temperatures means that the solute will dissolve faster. In chemistry, things we need to know about solutions are their concentration and the solubility of the solute in the solvent. Let's talk about solubility first. Solubility is the maximum amount of solute that can be dissolved in a certain amount of solvent. And a typical unit are grams per liter. And solubility is affected by temperature. So hotter water can dissolve more sugar than cold water. And the term insoluble means that that solute does not dissolve in that solvent. So for example, oil is insoluble in water. It won't dissolve. Let's take a look on page 58. So we're looking at sugar water again, and you can see if you put 1 gram of solute in 99 milliliters of water, you get a dilute sugar solution, whereas if I were to put 50 grams of sugar into 50 milliliters of water, I would get a concentrated. I would have this 100 grams of sugar solution. It would have the same mass, and it would be concentrated. So let's look at a table, a solubility table, to figure out how to read them. So here is your compound, and then the solubility in grams per liter. So salt, you can dissolve 36 grams salt in 1 liter of water at 25 degrees Celsius. Remember, the temperature does matter. Sugar is even more soluble, 2,000 grams at 25 degrees Celsius. Baking soda is less soluble, about 10 grams per liter. And you can see that chalk and vegetable oil are not soluble in water. You can see that oxygen has a very low solubility. It is 8.3 times 10 to the negative third grams per liter. So that would be 0.0083 grams per liter. So not very much, but that little bit is very important because that allows any aquatic animal to live. So we are glad that it is slightly soluble. So solubility, knowing if something is soluble or insoluble is good, but we also want some other ways to describe it, and that would be concentration. How much solute is in a solution? So solutions are described as dilute, concentrated. We can describe them in numbers as grams per liter, numbers as percent mass, or in numbers as molarity. So the dilute and the concentrated are pretty common sense. So let's go over the last 3 and how we would do that. So in chemistry, we need to know exactly how much solute is in a solution. Otherwise, maybe your experiment doesn't work, or maybe your experiment works a little too well. So we need to know exact amounts. So how do we calculate that? And please write these down. So first thing we're going to do is we're going to write this equation. Concentration in grams per liter is equal to the mass of the solute over the volume of the solution in liters. Then we're going to plug in the known quantities. We're going to plug in the known quantities and solve for the unknown and make sure our units match up with what they're supposed to be. So please write this down. The concentration of a sugar solution is 75 grams per liter. How much solution do you need if you want 11 grams of sugar? So the first thing we're always going to do is we're going to write down what we know. Okay, we've transitioned to our handy dandy smartboard and we're writing down what we know. So we know that the concentration is 75 grams per liter, and we know we have 11 grams of sugar, and we're trying to figure out how much solution. So I know I have 11 grams sugar, and I know I have a concentration of 75 grams per liter. And my question mark is how much? Well, what do we mean by how much? Coming up to our equation, we know our concentration, we know our mass, so that how much would be a volume. So we're trying to figure out our volume. So the next step in any problems are to calculate. First thing we're going to do is write the equation, plug in our known quantities and solve for the unknown, and make sure to check units. Please do write this equation down. The concentration in grams per liter is equal to the mass of the solute over the volume of the solution. So we know that our concentration is 75 grams per liter. And our mass of our solute is 11 grams. And then V is our variable. So I cannot just times 11 by each side, because then I've solved for 1 over V, and that's not a real answer that we want. So I have to have my variable up on the top, and to do so, I times V on each side. Whatever I do to one side, I have to do to the other. And then these V's cancel, and I'm left with V on the left side, but on the top of a fraction. It was a fraction if I put it over 1. So I have V times 75 equals 11 grams. I'm going to rewrite that. V, 75 grams per liter, equals 11 grams. And then I know I need to solve for V, so I'm going to divide each side by 75 grams per liter. And so these cancel. I'm left with V, and that is 11 divided by 75. So please get out your calculator and do that. Okay, if you got 0.1466666, you would be correct. And 75 has 2 significant digits, 11 has 2 significant digits, so my answer needs 2 significant digits. The 0 is a placeholder, so the 1, 4, the 4 gets rounded up to a 5 because the number after 4 is 6. So then we have to think about our units. So we know it's volume, so the unit's going to be liters. However, how do we know that? We got grams over liter. Well, if we're dividing by a fraction, we know that's the same as multiplying by its reciprocal. And then that could be over 1, the G's canceled, and I'm left with L, liters. So perhaps I want to do this in milliliters, because it's a lot easier to measure things out in milliliters than in 15 hundredths of a liter. So I would take 0.15 liters over 1 times 1,000 milliliters in a liter, 1 liter. And I am going to pause there, and you should get the answer, and I will tell you in the next video.